Are you able to
Yes,
read?
sir.
Yeah.
Yes, sir.
Yes, sir.
So today in the series, we'll get into the career statistics actually. So why it is important? What is it, and how is and what are the things involved in this? See, one thing we need to remember: engineering is all about quantification. So we need to make a quantitative assessment. That means we need to talk in terms of numbers. So that's very important. So we have seen that one of the figure of merit of the material which we are going to use is the conductivity. And we have seen that conductivity is decided by two factors. One is the carrier concentration and the other is the mobility. So we need to know the carrier concentration and the mobility to go forward to find out the conductivity. If you want to know the exact value of conductivity, we need to know the carrier concentration. So for that, we introduce the energy band concept. And in terms of energy band structure, we should be able to get the carrier concentration, and thereafter we will look into the mobility. So first part, we are trying to find out the carrier concentration. So that is what we are trying to introduce today. So what is the meaning of statistics? Any idea what is the statistics? What is statistics all about? Any idea about
So,
statistics?
Arranging the
number.
data.
Arrangement of data.
So actually, when statistics is involved, whenever you have a large number to handle. So naturally, when you talk about a solid, you can per unit volume, you have large numbers. So we need to invoke the statistics. We'll see that a large number of carriers are involved. So their history, independent history, and all those things. We'll see a little later about that. And so we need to get into the idea is to get the carrier concentration for finding out the conductivity, and various other parameters also will be decided by the carrier concentration. But so we get into that. So before that, we need to define these two terms, because we will be talking of carrier concentration under so-called equilibrium condition. So we need to know what is the meaning of equilibrium. We very often talk of a thermal equilibrium. Yeah, it doesn't mean that thermal immediately invoke the feeling of temperature, but it's not really about the temperature. But we generally talk of a thermal equilibrium or an equilibrium. And then, of course, immediately this may not be very important, but later on we will be seeing that we will be talking in terms of steady state. So need first we try to understand these two terms. What is the meaning of equilibrium? Anybody? Hello. Hello.
When no reaction is happening,
Pardon?
means when the state is stable.
Your audio is not clear.
State of balance.
State of balance.
Yes, sir.
Any is any other?
So when there is no surrounding change, it means the like
See, actually, when we talk of equilibrium, it is the equilibrium of the system. See, for example, we are talking about the carriers. So their states are not changed. Then we talk of an equilibrium condition, that it is not getting disturbed, because there are certain, if for example, you have a class, certain number of students are there. Let us say 50 students are sitting in the class. Their number is remaining intact. There is no activity. Then we say system is in equilibrium. Suppose a few people are coming in during the course of the discussion, so that means their number is getting disturbed. Again, there's some people. Another way is people can be moving out as the lecture is progressing. People are getting bored and they are moving out. Then that is also change from the equilibrium. Equilibrium means the system. It's actually you can see it in the from Newton's first law of motion. Actually, here in a physical system, we see it from point with the Newton's first law that unless otherwise a system is acted upon by an external force, it will remain it will remain in that static condition. So, whenever a force is acted upon a body, then the system may change. So, that is a non equilibrium condition. Under the influence of an external force, the system will get disturbed. There will be uh, facial as well as the spatial as well as the temporal changes can be there in the system. Then we say it is a non equilibrium situation. Now, so with that in mind, when we see there are two kinds of equilibrium possible. One is no forces acting on the system, and even with forces acting, the system can be in equilibrium. How? How it is possible that forces are acting, but the system is in equilibrium? Is it possible?
Equal force.
So
Equal and
Equal
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 and
force.
force.
opposite actually, because
Opposite.
force is a vector quantity, so it has to be equal and opposite. So if you have to, for example, if you are pulling a person in two different directions, if the pulling power is same or the force applied is same, the person will not move. It will remain. So very because why I'm saying is very often we will be talking of such an equilibrium where it is a kind of such an equilibrium is known as dynamic. In physics, it is known as the dynamic equilibrium. The earlier one where no forces are acting on the system, then we say system is in static equilibrium. But most of the time, we will be talking in terms of a dynamic equilibrium. Also, a simple equilibrium means most of the time it is a dynamic equilibrium, or thermal equilibrium means it is a kind of dynamic equilibrium. So here, in that case, as far as the semiconductor uh, material is concerned, or a device is concerned, dynamic equilibrium means some activity is going on, some rate, or at some rate the activity is going on, and there is an opposite thing which is happening at the same rate so that they cancel. For example, you can talk of an absorption, or electrons are emitted from or going from valence band to conduction band. You can associate certain emission rate associated with that. And suppose correspondingly there is, so you talk of in electronics or in semiconductor material, we talk of generation. We don't talk of emission because they are not coming out of the material. So in the case of semiconductor, we don't talk in terms of emission. We talk of generation. So electrons are freed and they are moving in the, as we have seen in the energy band picture, they can go to conduction band. So free carriers are generated. So that is generation. So that is disturbing the equilibrium. Suppose you shine light, or some form of energy is given. So electrons are liberated and they can go to conduction band. So that is one process. So we talk of a generation. So we can associate a rate with that. So we very often talk of a generation rate. And then suppose you remove the light. So then the system, the electrons in the conduction band will try to come back to the valence band and recombine with the holes present in the valence band. So that we talk of a recombination. So you can associate a recombination rate. If both the rates are same, there will not be any net change in the carrier concentration. So then we say the system is in equilibrium or thermal equilibrium. So any process with and if it is counterbalanced by a reverse process, the same rate, then we say the system is in equilibrium. So, or in a system is in thermal equilibrium. So that is the picture. Just like we have seen when two forces in opposite directions are applied on a system, two equal and opposite, then the system remains static. So similar situation. So if your generation rates and recombination rates are same, then your system will be in thermal equilibrium. So that is the equilibrium we will be talking of. And what is steady state? So what is there any difference between equilibrium and steady state? Yeah. Any idea about steady state? Hello.
Sir, somewhere energy is put on the system.
What is the meaning of steady state?
Kind of, sir, whatever any energy put on the system to maintain a higher energy level.
So that is steady state.
Yes, sir.
Steady state actually means it's actually a transient thing. So suppose you apply or system is disturbed. For example, you have shine light and remove the light. So that initially the system was disturbed, and so there will be some process taking place because of the system got disturbed. It's like putting a stone into a pond. Waves will be created, and then you are putting only one stone and then you leave it. So after a passage of certain time, again the system will come back to what is known as the steady state. That means a disturbance has taken place, or you have disturbed the system externally, and the disturbance is removed, or the external force is removed. Then and a large amount of time has elapsed after that. Then we say it is a steady state. Steady state is normally we are talking about the time. So typically physics says a steady state means t tends to infinity. When time tends to infinity, see at time equal to zero, some event has happened. Now time is infinity, then we say the system is in steady state. So this is these are two different terminologies. One is equilibrium, thermal equilibrium. Other one is the steady state. Steady state means as a large amount of time has gone by after the initial disturbance has taken place. So we talk of mathematically we talk of t tends to infinity, and initially it was t is equal to zero. So t is equal to zero. Some means uh, some event happened, and now a large amount of time has happened or passed by. So then we say it is system is under steady state. So now the advantage, see now again infinity is different for different people or different cases. Actually, in semiconductor systems, the transient event takes place in picoseconds or femtosecond. So 1 second, and normally we talk in terms of few seconds actually. So when a few seconds have passed, as far as the system electronic material or device is concerned, it is a steady state condition. So 1 second is an infinite amount of time for a semiconductor material. For us it may not be. For us decades or centuries might be the large amount of time. Yeah. So these two concepts one should be clear. One is the thermal equilibrium, and other one is very often we will be taking advantage of these things we will be discussing, especially when we discuss about the characteristics of the device. We bring in the studies because very often the devices are excited, some impulse is given to, and then how it performs. So that way we have to see that. So similarly equilibrium. So because we need to start from a stable system, so that is why we start with the equilibrium, because the carrier concentration is defined at equilibrium, then it can be disturbed. So equilibrium disturb means the carrier concentration can be changed by disturbance. So then we can talk of that. First we start with an equilibrium situation. So what we are discussing today is valid for the equilibrium situation. That means there is no change of carrier concentration at because what we are trying to say is that way the stability is maintained or equilibrium is maintained. So now equilibrium distribution of electrons. See, we actually this is I'm just a slight. Sorry. The first that equation you should start with the last line, that is n. The carrier concentration is decided by two factors. One is the density of states. See, actually, we have seen a continuum of in the energy band. So there are what is the uh, density of energy states per unit volume per particular energy range. That is the meaning of density of states. And then second part is what is the probability of occupying that state. So these two, the product of these two will give me the carrier concentration. So we need to know density of states. See, for example, if I want to know the carrier concentration in conduction band, so I need to know what is the density of states in the conduction band, and then what is the probability of occupying that particular energy state. So the product of this for that given temperature will give me the carrier concentration. So that is how we go about so that is how you see you are bringing in the energy band, because we have seen so far we last many lectures we were devoting to energy band. Now energy band structures, how they are used, they are basically helping us in finding the density of states. Then once we know the density of states, say for example, if you know the density of states in the conduction band, you can find out the carrier concentration in the conduction band. Similarly, if I know the density of states in the valence band, I can find out the it will help me in finding out the whole concentration in the valence band. And the second factor I need to know is the probability of occupying that or that state. So this product of this integrated over all the energy range will give me the total carrier concentration. That means it will be integrated over all the, in the case of electrons, it will be integrated in all energy range in the conduction band, and valence band. In the case of holes, it will be integration will be carried out with the energy ranges in the valence band. So that is how we go about it. This so this slide should have been there. Yeah. So okay. Now we come to the second term first. That is the second term here, the probability of occupancy. So that is given by this is how where the statistics is involved. So this is basically given by the probability of occupancy is given by the distribution laws. Like you have, try to understand, you have various energy states available in the material. What is the probability of occupying? So there is you can discuss in terms of distribution laws. So just like my favorite example is a classroom situation. You have benches available, and typically it is expected that from a front row it will start occupying, and then it will go to the back front, because teachers will be standing in the front. So naturally, first row will be filled first, and second row like that it goes. So there is so that is the picture we should keep it in mind. So how what are the probability of this occupying a particular energy state? So these are this is given by the distribution laws. So these are three distribution laws are quite popular. One is the classical one, which was given by Maxwell's Boltzmann, and the second one is quantum, that is Fermi Dirac. Important difference between the classical and quantum is the last two are the quantum mechanical distribution law. The first one is the classical one, the oldest distribution law. It was is used for the gases, basically gas molecules in the development of the kinetic theory of gases. It was extensively used. So this is there. It is for the distinguishable particles actually. So that we will not go into the details of this derivation of these distribution laws, but we will define them, and we will basically we are interested in the Fermi-Dirac distribution, and we will just see that what is Fermi-Dirac distribution and how it is different from other two. That is all we will be discussing in the today's presentation. I will not go into the derivation. One can always derive these distribution laws and invoking various physical principles, one can do that. We'll not be going into that. So somebody who is interested in physics about it, they can go and do that. So so I will talk of a Fermi function is nothing but is a probability function. So so this is the probability of occupying a particular energy state E at a temperature T. So this is again one thing we need to understand. All these distribution laws are defined for the equilibrium. So under equilibrium condition, what is the probability that an available state of energy E is occupied? And it is given by this expression. That the Fermi function is given by this. And here, and it is around the energy, Fermi energy, that is EF. So EF is the Fermi energy, and the K is a constant, and the temperature, etc. So this is how the Fermi function is defined. Now we need to understand one thing. Uh, a class of particles which obey Fermi, there are two categories in quantum mechanics. Two categories of particles are defined based on which statistics they follow. The the particles which obey Fermi-Dirac statistics are known as fermions, because of course it is after the Fermi. So examples are electrons, uh, protons, positrons, etc. So the general guideline is the particles which obey Pauli's exclusion principle. Have you heard of Pauli's exclusion principle?
Yes, sir.
What is it? What is Pauli's exclusion principle? Yes.
So two electrons are only allowed in a state with opposite spin.
Yeah. So the moment you say the states are different, actually. See, Pauli's exclusion principle says that no two electrons can occupy the same state, because at least their spin has to be different. The moment you say the spins are different, their energies are different. So that is how in a single state, two electrons can occupy, because one, at least their spin is different. So spin also represent energy. So Pauli's exclusion principle invokes that particles with half spin, they cannot. It is applicable to particles with half spin. So that is the for those particles obey Pauli's exclusion principle, and particles which obey Pauli's exclusion principle, we need to use Fermi-Dirac distribution. Actually, during our MSc, we have derived all these Pauli's exclusion metrics, all those derivations we used to do in our masters in physics, actually. And even all this derivation of the Maxwell distribution law, Fermi-Dirac distribution law, and the third one is the Bose-Einstein. All those things we have done during. Of course, I never understood anything of that time, but now today I was just thinking, all those days we used to derive all those things without understanding anything. Anyway, so so this is the important thing is for particles which obey Pauli's exclusion principle, we use Fermi distribution law, and this is then you can talk of just see at 0 Kelvin, if the large energy when the E is large as compared to F, the probability of occupation of that state is 0, and when E is less than EF, the probability from that mathematical expression we can derive that. So you can see that at absolute zero, all the states below Fermi is occupied because the probability is 1, and above Fermi level all are unoccupied. That is the meaning, because the probability is 0. So that means at 0 degree Kelvin, the states above the Fermi level are empty, and below Fermi level all are occupied. That is a picture you get from the at 0 degree Kelvin from the Fermi-Dirac distribution law. And then again, one can see it at different temperatures also. One can always, because you have the function, you can apply. So it's nature. As you increase the temperature, you see that. Otherwise, it is a step function, and then you can see that it varies from a deviation as you increase the temperature. Now, so I talked of Boltzmann distribution. Boltzmann distribution is when E minus Ef is much larger than Kt. Kt, what is Kt? What is Kt dimensionally? Yes, what is Kt?
Energy.
Electron.
Yeah, Kt is the thermal energy, because actually it will be definitely it has the units of energy. So it either in electron volts or joules you can express them. So Kt is the thermal energy at any temperature T. What is the corresponding thermal energy? One can calculate by multiplying it with Boltzmann's constant. So if E minus F is much larger, then you can mathematically you can see that the exponential factor can be written as Fe can be written as E exponent minus E minus Ef by Kt. So this is nothing but if you go into the Boltzmann distribution law, then we see that a Fermi-Dirac distribution simplifies or comes down to Maxwell's Boltzmann distribution when this condition is met. That means E minus Ef is much greater than E. That means the number of states are more, higher energy states are more, and the number of electrons are less. So again, I will use this analogy here. So you have a classroom where the large number of states are available, but the students are very less. Typically, it happens in my class. We have a large lecture room, but the number of students are hardly 3 or 4. So then we need not worry about how to place them, because large states are available, large number of states are there. So we need not worry about the Pauli's exclusion principle when large number of energy states are available. So you can Fermi-Dirac distribution approximates to Boltzmann distribution when this condition is met. And we will see the way I'm saying this, very often we will be using this instead of the first expression for the Fermi-Dirac. We will be using this, that is F is approximately equal to E minus E minus Cf by Kt will be the distribution function we'll be using. If it's so it is same as the Boltzmann distribution function. Now, I just wanted to mention about a little bit about the other distribution function, because you won't get an opportunity. That is the Bose-Einstein distribution law. That is the difference is you see this Fermi function. So it is if it is -1 instead of 1 plus, then we say it is the Bose-Einstein. And the Bose-Einstein distribution law is generally used for particles with integral spin, like so they are known as bosons. It could be molecules, it could be like photons, phonons, etc. The thumb rule is particles which doesn't obey Pauli's exclusion principle, or particles with integral spin, they follow the Bose-Einstein distribution law. It was proposed by Bose, and then he wrote to Einstein, and then together they wrote the paper. So that is how this is popularly known as Bose-Einstein statistics. And the particles which obey Bose-Einstein, in order to credit the contribution of Bose, they are known as bosons. So which Bose? You know the full name of the Bose? The Bose was done this with worked with Einstein. This just for the general information. What is the name of the full name of the Bose? Hello, hello,
Sir, is it
hello.
Sir, is it Jagdish Chandra
Pardon?
Bose?
No. Any other Bose you know? J.C. Bose never worked with Einstein actually. I think J.C. Bose was much before Einstein's time. Even though he has done, he was a polymath, he was involved in botany, physics. In fact, he has developed this wireless system, radio communication, so all those things. But then
So
he never worked. Yeah.
Bose.
Yes. Yes.
Satyendra Bose.
Yeah. 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 It is S.N. Bose actually. So they have. He has basically a physicist. So he has to work like with in collaboration with Einstein, and then probably the Dirac gave this name bosons to those particles which obey the Bose-Einstein style. That so this again we have recently seen that 2 3 years back there was a development about Higgs bosons. Higgs bosons again a very important discovery or invention. I don't know what I should say, discovery or invention, because the right word should be discovery, because that is again like they also follow the Bose-Einstein uh, uh, distribution. And God's particle is something which gives. I'm not going to the details. One can always go and read. The Higgs boson is something which gives mass to the in the particle physics, which the thing which give mass to the thing is Higgs boson. So that is why they are very often known as the God's particle and things like that. Anyway, so let us go back to our discussion, the Bose distribution. So this is the Boltzmann. So very often we will be talking of the when the carrier concentration is less, we can talk of Boltzmann distribution. So Fermi-Dirac distribution will be approximated to of Boltzmann distribution. Only thing is when you have a large concentration of carrier, very often in microelectronics it happens, you have a large concentration of carriers, then Fermi-Dirac distribution law may have to be invoked. So we will see that later on, such semiconductors are known as degenerate semiconductors, where large concentration of carriers are there, because they degenerate like a metal. Actually they behave like they degenerate into metal. So very often they are known as degenerate semiconductors if the carrier concentrations are quite large. So first thing is they will be known as degenerate semiconductors. Second thing is there we will have to strictly use Fermi-Dirac distribution law. You cannot approximate it to Boltzmann distribution. So these things you should keep it in mind. We'll talk about the degenerate semiconductor later. So the density of states, the carrier concentration will be very large, close to the valence band and the conduction band edge, actually. So we talk of now using this, the concentration of electrons can be written as in the electrons in the conduction band can be written as a constant density. Density is the density of states, and that is known. I'm not going into details of how we got this NC. So NC multiplied by the distribution function will give me the total electron concentration, where NC is can be expressed in terms of the effective mass. You see, effective mass is coming into picture here. So NC is decided by the density of states is decided by the effective mass. So and the temperature, of course. The other things are constant. So this is the density of states of electrons in the conduction band multiplied by the Fermi function will give me the electron concentration. A similar argument can be used for holes. So what will be the probability of finding a hole in a valence band? Any answer? So
One
because
minus
again, yes, pardon.
one
Zero.
minus probability of
Why one minus?
so probability can be maximum can be one.
No, actually, you are right. Why it is one minus, but the reason is because it is absence you are looking for, absence of electron. So probability of finding is 1, then probability of not finding is 1 minus something. So that is why, because you are trying to find out the absence of electrons. The holes are nothing but absence vacancies of created by the electron. So that is how we go about it. So again, the whole concentration will be given by density of states in the valence band and multiplied by the Fermi function. Of course, 1 minus the Fermi function here. That is the probability of finding the holes in the valence band. So again, we can do the bit of mathematical jugglery. So we can see that P naught will be the whole concentration in valence band is P naught is and the density of states multiplied by the Fermi function. So it is again the density of states will be decided by the effective mass of holes in the valence band and the temperature. So the other parameters are constant. So you can see that. So then multiplied by the Fermi function or the probability function will give me. Actually, it is same as the Maxwell function. So we simply say probability function. That will give me the carrier concentration of holes in the valence band. Now I do a bit of mathematical jugglery here. I have both. Yeah, I mean, so we are talking about the pure semiconductor. So far, we have not touched any other things. We are talking about the pure semiconductor. So Ni is the electron concentration we have found. Electron concentration in the conduction band we have seen, and similarly, we are talking about the whole concentration in the valence band, and then EF is replaced by EI. So that is EI is nothing but the Fermi level of the pure semiconductor, or we say intrinsic semiconductor. I will say it is an intrinsic semiconductor. There is no additional impurities present. It's a pure one. So that is why it is known as the intrinsic one. So EF is replaced by EI. So both the cases. Now what I do is I take the product of N and P. So we can see that the product will be so easy. My like you can it is visible to you. So and NC and NV the product is constant. So I can see that the product for a given temperature, because for a given temperature the band gap is also a constant. So the product of N and P is a constant. So this is very often known as the law of mass action. So this will be very extensively used, and then from that, and most of the material for the given temperature Ni is known. If you go back and see the table I've given you earlier about the semiconductor materials, Ni squared or Ni of the material are known. So that way one can find out N naught, and then you can find out once you. This is a very useful relation. I'm not going to the utility of this right now. We'll see that it will be very extensively used to find out the carrier concentration, because carrier concentration is one parameter which is very important throughout in deciding the properties of the material and devices. So this relationship is very important. We will be using this relationship extensively hereafter. So the product N and P is known as Ni squared. So of course it depends on the temperature, and then slight dependence on the band gap also, because band gap anyway will change slightly with the temperature. So this is very often known as the law of mass action, analogy taken from the chemistry. Yeah. So I think this is what I wanted to discuss here today. So one thing, as far as the band diagram is concerned, we should know that EI or EF, the Fermi level will be near to the middle of the band gap, because you have a conduction band and valence band, and there is a forbidden band. So the energy state corresponding to Fermi level will be in the middle. Actually, this is the best question. So I think I'll stop it here. So we have these questions. Anyway, I'll be uh, posting it. You can note it that this is for the next week. So these questions you can note down from the slides later on. So these are some of the things which we have discussed, so that you think beyond what we have discussed. That is idea. So the the energy calculations and the things like that. So this some of your lower level classes knowledge will be necessary to solve these problems. So then one numerical I am giving you, two numericals in fact. First question and last one. You need to find out the intrinsic Fermi level in an undoped semiconductor, and you have to prove that it is in the close to the middle, and you have to find out the position of that, and you have to show that it is not exactly in the middle, it is slightly above middle. So that question you can these questions you can work out. Yeah. Yeah. So questions, any questions related to what we have discussed?
Sir,
Yeah.
sir, you said we will use Boltzmann distribution when the carrier concentration is large. Sir,
No,
how
sorry.
much is?
No, sorry, opposite.
Oh,
If I said
oh, sorry.
large, it is wrong. It is low, because
Oh,
see
sorry, sorry.
see actually, yeah, the thing is you have to understand what is happening is you have a large number of states available, and you have a carriers. How they are distributed, that is the probability function is deciding that. But when the number of carriers is small and energy states available is large, then you don't need not worry about how they are distributed. That is why that restrictions. See how Fermi-Dirac distribution was different from Maxwell distribution because of the Pauli's exclusion principle. If the number of carriers are less, we need not worry about the Pauli's exclusion principle. That is the argument I am using. Okay.
Yes, sir, I got confused. Yes, sir. Thank you, sir.
Yeah. Yeah. Any other thing? Hello.
No, sir.
Ah. Yeah.
No, sir.
Now we. Yeah. Prashant want to say something.
No, sir.
So now we can take up those assignments. How many of you have done the assignments? Try to do the. I mean, of course, Nithya has sent me the file. Others have not sent the file, so I don't know what is the status of about others. Anybody attempted those assignments?
So he has not
And
told to
actually,
send it, so he has not sent it.
Pardon, I cannot hear you.
Sir, actually he has not told us to send it, so he has not actually.
No, but I mean, the important thing is not about sending. Whether you have tried or not, that is the question. All the
Yes,
sir,
assignment,
we
whether
have
you
we
have,
tried.
tried, but we didn't write it on. Just we
your audio
took
is.
the research.
I am not able to hear you. Can you say it a bit loudly? Yeah. Hello.
I'm typing in the
Hello.
chat box.
Pardon.
Typing in the chat box.
I'm not able to make. Why can you type it on the chat box?
Yes, sir, he said that only he's going to type that in chat box.
Okay. So, all the problems you could understand, and you could do it. See, for example, let me take out that file. I have it here. I think somewhere here. Okay, let me take. Ohm's law. What was the application, possible engineering applications of Ohm's law you proposed? I said minimum three. So let me start with Nithi. Yes, Nithi is there.
Yes, sir.
What are the applications, engineering applications of Ohm's law you could think of? That was the first question, no?
Yes, sir. Sir, I, sir, I thought of designing as in designing, so designing applications like electric heater or
Yeah, then one is an electric heater, right?
uh,
Even though it is a power, but then still
yeah,
ice. Yeah. Then
and then other one I thought that while we make device, we calculate its power consumption, so there we use it uh, for any device.
see,
Uh,
can, yeah, any, both the cases power. So it is same. You're
yes.
dissipating power. That's all. Any other?
Yes.
Third one? First and
So
second are
that
similar anyway. Yeah.
that is also somehow related to power. So
What
now
is
I
third
think that,
one?
sir, while designing mobile chargers or laptop chargers,
Hmm.
the amount of current we need, we have to calculate it by Ohm's
No,
law.
there
Like we
that
have,
is different. There it is not the power. You are limiting the current. It is can be
yeah,
used to.
yes,
Yeah. Yeah.
yes, sir. These three
Yeah.
applications I wrote.
Yeah, you keep
Yes,
it
sir.
in mind whenever you see an application. You try to recollect that and note it. I mean, remember that. And this is just giving you an example, but you can think more application. There are many more applications one can think of. And when you come across it, you should at least realize, okay, this is an application of Ohm's law. And now coming to Prashant, what are the possible applications? Prashant, are you there?
I wrote them in the chat box.
Pardon?
He wrote in chat box, sir.
Yeah. Potentiometer, heater, and meter bridge. Yeah. Potentiometer is another example very often because we use potentiometers to drop the voltage and I mean basically you are dividing the potentials. The potentiometer is a good example. Heater, of course, we have already taken. Meter bridge to limit the meter bridge. Which way you are planning to use, or which way it is used in meter bridge, Prashant? Yeah, Prashant, are you able to hear me? Voltage of unknown source. Actually, it is basically again a potentiometer kind of application, or is it different? Anyway, it's a potentiometer kind of thing. Yeah. Anyway, so my idea is keep this thing in mind. Whenever you see some particular application, you see that what how it is being done. For example, you will see that even in your uh, many of the cases, the for current limiting, one can do that. Biasing, you are almost all transistor circuits. You need biasing. You draw so biasing is done using resistances. Then well, limiting current. For example, you have a LED. You want to limit the current. So again, we use a resistance. So one can think of application. I'm not a great engineer, so I can't think of lot many applications. But we can see that. But when you see a particular application, you should okay, you should be able to connect actually. The bulb is again, it's a power dissipation and then heat. Yeah, bulb is an example. Yeah, right. Yeah. Nekha, any what are the kind of applications you thought of?
So fan regulators.
Pardon, I can't hear you.
So fan regulators.
Fan regulators, yeah, old fan
Yes.
regulators, right? Good example. But today we don't use. Nowadays it is not used. Earlier it was used in fan regulators because the current regulation was done. Yeah, good
And
example.
and
Yeah,
and so second one is electric kettle.
electric.
Kettle.
What is it? Can you chat? Can you
So
type it on the?
electric kettle in which we boil water or make Maggie.
Okay,
Sir,
I mean I could not.
kettle,
Uh,
electric
Kettle. Oh, okay.
kettle.
Yeah. It's all heater actually. Both Prashant and Nithya has already said the heater. So it is kettle or in a different form. Same principle is used. Yeah, these are different applications. Yeah. Second one. Okay. That anyway, you should keep that thing in mind. That this was just to give you an idea about turning physical laws into engineering applications, because we said that the role of an engineer is the first lecture I was emphasizing on this aspect. The role of an engineer is converting physical laws into uh, practical applications, or you can developing uh, applications which can be put into use by in our day-to-day life. That was the idea. So this was a simple example which I mentioned. Now, second one, it is yeah, at least one example explain the importance of abstraction in engineering the product. Yeah, we will take the electronic case. So that is why I said the use of IV abstraction. But you can, there are other cases also, but then let us use IV abstractions. Yeah, let me start with again Nithi.
So IV characteristics, for example, if we see IV characteristic of a diode, then we can tell that it can be used as a switch or rectifier.
Yeah.
There
So
we can
he,
do it.
yeah. So here
Uh, uh,
abstraction, see, yeah. Anyway, you elaborate. Yeah, that is fine.
no, sir, no, sir. You speak.
Means here, see, the abstraction means you have characteristics. So anything which gives, see, we know that PN junction diode gives these characteristics. Your metal semiconductor junction gives these characteristics. Your simple vacuum tube diode gives this kind of characteristics. So abstractions means the characteristics is the abstract here. So anything which that gives that kind of a characteristics can be used as a switch, can be used as a rectifier. That is the idea. So today you might be using uh, vacuum tube as a rectifier. Tomorrow, that is, in fact, that is what has happened in electronics. Earlier, in 20s, 30s, 1930s or so, people were using vacuum tube diode for making rectifiers. Then they found that better PN junctions diode can give the same kind of characteristics. So they are used increasingly. They are being used for this. So the abstractions means you are interested in the only characteristics. Whichever device gives you that kind of characteristics can be used. For example, the diode example, if you see, it was initially vacuum tubes were used, then PN junctions were used, then you have used metal semiconductor junctions are being used, and even some of the transistors, that because you know that transistors have a PN junction, so that can be used. So the important thing is the characteristics abstraction. So application is derived from not from the device but from the characteristics. So that is the meaning of the abstraction. Yeah,
So,
Prashant. Yeah, you wanted to say something, Nidhi?
sir, is frequency response curve of a device also a characteristic?
Yeah, definitely.
Like
Because
for
see, we will see. Even though I have not mentioned about it, frequency is because the characteristics can change with frequency. So if see, for example, very often in electronics it happens. Your signal you are applying not DC anyway. You are applying, and signal means very often it will varying in frequency. So, for example, you take your some song or something. It is not a single frequency signal. Actually, there will be multiple frequencies, and if the characteristics of the device changes with the frequency, so then your performance of that circuit will be affected by the so frequency response is a very important factor. Even though I have not mentioned it, it is very important. So that also should be kept in mind. See, again, for a given application, we will see these parameters. Actually, one is the power consumption, second thing is the frequency response. Which has a higher frequency response, or we talk of bandwidth, then that is a better choice. So because that it can uh, cover that much frequency range. For example, the multimeter you are using, again it has a bandwidth actually, so it won't be equally useful for all the frequencies. You have to we have, that is why we need to know up to what frequencies it gives a decent response. So frequency is a very important parameter. So that also, even though I have not mentioned, it is since in electronics we deal with high frequency signals, so the frequency response of the device becomes very important. Yeah. Yeah, Prashant.
He wrote in chat box, sir.
By looking at temperature conductivity characteristics, we can use it for um, measuring temperature, right? No, so that was first related to the first one. So the thing here, when I talked about this abstraction means, the important thing we need to understand is, or as the example I selected, for depending upon the characteristics you can replace. Actually, that is the meaning of abstraction of the uh, characteristics actually. So for example, if you see that BJT was used, or initially pentode was used as an amplifier, then it was pentodes were replaced by transistors, that is BJT. Then now BJTs are replaced by MOSFET actually. And but if you look at the characteristics, they are all identical. Of course, the voltages, the currents you can get might be different, but the nature, I'm talking about the nature of the characteristics. In the case of vacuum tubes, you might be going to voltages of hundreds, and the currents might be running into milliamperes to amperes, whereas in transistors, it will be in few volts, 10 to 20 volts, or then current might be in milliamperes. But if you look at the characteristics, they are similar. And you can use vacuum to pentode as an amplifier, or you can use a BJT as an amplifier or a MOSFET as an amplifier. And then if you see, you have seen that MOSFETs has many advantages as compared to your BJT or vacuum tube. So they could be replaced. So you should be always looking at the characteristics, and then you conclude, okay, this particular device can be used for this application. So that is the important. So tomorrow, if you are coming out with a new device which gives MOSFET like characteristics, so then I can replace MOSFET with that if its features are better. For example, it is having less dimensions or less power consumptions. I can replace MOSFET with that. That is the idea of the abstraction. Yeah. Neha, you wanted to say something?
Hello.
Yeah.
So on the basis of gain characteristic, we can differentiate what kind of amplifier it is, whether it is a buffer amplifier, narrow band amplifier, or any kind of any amplifier.
Yeah, but the idea here was, see, the abstraction in what I meant was like replacing one with the other. Actually, so you are talking about the application, particular characteristics. You will from that we will decide whether it can be used for a particular application. That is fine. But we want to replace one device with the other. That is how our electronics has progressed from vacuum tubes to integrated circuits. The more or less the characteristics remain the same. Our applications remain the same. For example, we needed a rectifier always. Only thing is the device which we are using for rectification has changed over the time. Today we may not be using a diode for making a rectifier within the integrated circuits. We will be using a transistor instead of doing that, because we are focused on the characteristics only. So anything which gives me a rectifying characteristics can be used. That was the idea behind that question, actually. Okay.
Yes, sir.
Yeah. So the last question was maths in engineering. Yeah, you want to say something, Neha? Is
Sir, we use mathematics to find the Laplace and Fourier transform and use in discrete sampling and
see actually everywhere. See everywhere you are using maths. So because all the, see for example the carrier concentration, we have simplified, and then we have found. So whether it is a differential equation, you solve the differential equation, your engineering problem. So you can talk of 101 examples of that. I am not going into detail, but you should be observing those. My idea is you should start observing how maths is being used in the engineering application. You have differential equation, with the solution of the differential equation will give me the some uh, solutions to my practical engineering application. So that is what we should be looking at. Yeah. So now the last one, could you do that? I mean, I think she has done it. Niti has done it. Actually, last numerical there was Neha. Have you done it?
no, sir.
Okay, you try to do that.
Yes, sir, I
Okay.
tried to do that.
Yeah. Yeah. So Niti, you have done that problem of that microprocessor,
Yes,
isn't
sir.
it? Yeah.
Yes,
So
sir.
what is the why I gave that? See, the you have done it, so, but
Yes, sir.
why I gave that problem?
Sir,
Are
because
you?
if sorry.
Yeah.
So because if we that the main idea was that if we use the transistors instead of integrated, uh, so, it would be practically impossible to
Yeah. So
um,
that is a, yeah, that is a good observation. That is what for that only I gave that, because you can see that the weight will be in tons, then the power consumption is in hundreds of kilowatts. The area it is going to occupy, it is
yes, sir.
practically impossible to make a micro, because we know that today when we talk of microelectronics, the heart of any integrated circuit is the microprocessor. You are giving intelligence and everything. Today, any system you talk of microprocessor is there, and you cannot make a decent microprocessor with discrete components. So that was the idea. You have perfectly got the point. Yeah. Okay. Anything
Okay,
else?
sir.
No,
No,
sir.
sir.
So okay. So I think I'll conclude today. Neha, you wanted to say something?
No, sir.
No. Okay, then I will call it a day then. Okay.
Thank you, sir.
Okay. Oh, welcome.